everyone, and thanks for watching Edupedia World Videos. In this video, we'll start a new topic called thermal expansion. I'm sure you're familiar with the basics of thermal expansion. Let's say we have a rod which is 1 meters long. We know, and it seems like common sense to us, that when we heat this rod, the temperature is going to rise, and that will end up resulting in the length of the rod to increase. And it might go, if it's kept at the left end, it might end up increasing its length by a little amount. It's usually a very small amount, maybe 1 centimeter or even smaller. Right. So our goal now is to quantify this and understand what temperature difference causes what change in length and so on. So the very first formula I'm going to write down is the definition of something called the coefficient of linear expansion. It is denoted by alpha and it is defined as 1 by L delta L by delta T. Right. So delta L by L would be the fractional change in length of a particular object. Remember, right now we're talking about one dimension. Later we'll move on to areas and volumes as well. Right now just assume we have a one-dimensional rod. So if the initial length was L, finally it becomes L plus delta L. Then delta L divided by the original length L is going to be the fractional change in the length. Right? If the length was 1 meter and it increased by 1 centimeter, the fractional change in length is going to be 1 by 100. Delta T is a small change in temperature which caused this change in length. So if the length became 101 centimeter from 100 centimeter when the temperature was increased by 20 degrees centigrade, then we could write 20 here, and this will be 1 by 100 divided by 20. Right? Now an important thing to note in this definition is that temperature itself never comes into the question. It is always a change in temperature. It is always delta T. So because of the fact that it is always a change between two temperatures, you can either use centigrade and Kelvin. It won't make any difference. The difference between 20 degrees centigrade and minus 5 degrees centigrade is exactly the same as the difference between this particular value in Kelvin and this particular value in Kelvin. Both of them will be 25 units. Because this is 20 plus 273, this is minus 5 plus 273. When we subtract, it will cancel out. Right? So this is the most important quantity, and it denotes how much an object's tendency is to expand. If on heating an object it expands by a pretty significant amount, then alpha would be large. On the other hand, if for a small change in temperature the fractional change in length is very small, then alpha would be small. Right. So let's just look at this equation further and try to derive some results from it. Alpha is 1 by delta T delta L by L, or sometimes it is also written as 1 by dt dl by L. Right. So what that gives me is dl by L is equal to alpha dt. Now I can integrate both sides because I know alpha is a constant. Let's say initially the length was L naught, finally the length becomes L. Initially the temperature was T naught, final temperature is T. So what that gives me is the log of L by L naught is equal to alpha into T minus T naught. Right? Or I can write this as L by L naught is equal to e to the power alpha T minus T naught. Now this is the actual equation, but we can further simplify it, and for that I'm going to use the power series. I'm not sure whether you're familiar with it or not. You might be familiar with it through your mathematics classes. If not, just assume that what I'm telling you is true. You will learn it soon enough in maths. So there are power series for all standard functions such as e to the power x, log of x, sin x, cos x. E to the power x for any particular value of x can be written as 1 plus x plus excuse me, x square by 2 factorial plus x cube by 3 factorial plus dot 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 going on till infinity. We know that the later terms will tend to contribute less and less because of the factorial in the bottom. This is true for any value of x. Right. If x is very small, then the higher order you go up to, the less significant it will be, right? And if assuming x is very small, infinitesimal, then we can simply write e to the power x is equal to 1 plus x, because x square by 2 will be much smaller than x if x is much smaller than 1. So this is the result I am going to use here. But when can this result be applied? Only when alpha times t minus t naught is small. Right. So this is the first important thing we need to know. This particular formula is valid all the time. But a formula I'm going to use right now, which is derived from this, which is the formula that you will be using 99% of the time, is only valid for a particular special case, that is alpha delta t is very small. What is alpha delta t? It is the fractional change in length. So everything we do from this point onwards will only be valid for very small changes in length. If an object of 1 meter ends up having a length of 1.5 meter, none of this will be valid. But if the object of length 1 meter ends up having the length of 101 centimeters, what we say would be valid, right? So let me just derive the equation here itself. This tells me that L by L naught is equal to 1 plus alpha times t minus t naught. Or what we can say is L is equal to L naught times 1 plus alpha delta T. Delta T is the change in temperature. Right, so I'm going to write that again. L is equal to L naught times 1 plus alpha delta T. Right. Now this is our holy grail. This is the result from which we will derive every other result. But you need to know the importance of this result and when it is valid. It is only valid when alpha delta T is much smaller than 1. If alpha delta t is very small, the length will be increased by a very small amount and we can use these results. If alpha delta t is large, in that case we would have to use the original formula where L by L naught would be e to the power of alpha delta t. Right? So this is a standard formula, and let's look at an example of this formula. Standard simple example. I have a rod of length 10 meters, let's say, and the alpha of the rod is 0.0002 per Kelvin. This is the unit of alpha. Alpha delta t is fractionless, remember that always. Alpha delta t denotes the fractional change in the length. So alpha delta t is dimensionless, that means the dimension of alpha is per unit temperature. So 0.0002 per Kelvin is exactly the same as 0.0002 per centigrade. Only in this specific case, remember that, because we are always talking about the change in temperature. This is not true always. In most cases, you cannot interchangeably use centigrade and Kelvin, as for example in the ideal gas equation, you can't use centigrade in that. But when it comes to change in temperature, since centigrade is just the Kelvin scale shifted by a slight amount, both of them are valid. So let's say initially the rod was at temperature 50 degrees centigrade, finally the temperature was at 70 degrees centigrade. What is the final length of the rod? So the final length will be 10 times 1 plus 0.0002 times 20, right? Because 20 is the change in temperature, which gives me 10 times 1 plus, hang on, 1 0 will go away, 0.004. So 1.004, which is 10.004. Sorry, 10.04. So we see that the temperature will be increased, the length will only be increased by 4 centimeter, quite a small amount. So this is the standard formula with which you will be able to solve the simple questions. Now let's move on to slightly complicated questions. I said that this was for one dimension, we need to do it for area and volume as well. So let's just look at a square plate in terms of a two-dimensional object. The square plate, let's say it has a length L on both sides, right? So if we increase the temperature, then the length of each side would be L naught times 1 plus alpha delta t, right? What is the area? Area at any time is L squared. That would be L naught times 1 plus alpha delta t whole squared. So L naught squared 1 plus alpha delta t whole squared. That can be written as L naught squared 1 plus 2 alpha delta t plus alpha delta T whole square. Now again I'm going to use the same thing, which is that alpha delta T is very small. In most cases when we talk about thermal expansion, unless specifically stated otherwise, you can assume that alpha delta T will be small. If alpha delta T is small, I can neglect this term in front of this term because it is the square. Or I could have just used the binomial theorem here, and 1 plus x whole square would have become 1 plus 2x for x being small. So what I get is A, the new area, is equal to, now L naught square is the original area because the original length was L naught, right? So it is equal to A naught times 1 plus 2 alpha delta T. We write it usually as A naught times 1 plus beta delta T, where alpha is the coefficient of linear expansion. Similarly, beta, which is equal to 2 alpha, is the coefficient of surface expansion. And it is 2 times alpha. So if alpha is 0.001, beta will be 0.002. Right. Let's look at 3 dimensions now. I'm not going to draw the figure. It's just a cube of side L. So L will be equal to L naught times 1 plus alpha delta T, which means volume, which is L cube, will be L naught cube times 1 plus alpha delta T whole cube, which again can be written as L naught cube times 1 plus 3 alpha delta T, because the other two terms will be very small, which gives me V is equal to V naught times 1 plus gamma delta T, where gamma is equal to 3 times alpha is the coefficient of volume expansion. So the coefficient of linear expansion is the most fundamental quantity. It is generally known for particular materials. But if you know the coefficient of linear expansion for iron, then you know the coefficient of volume expansion for an iron cube, as well as the coefficient of surface expansion for an iron plate. Right? The coefficient of surface expansion will be just the twice of the linear expansion, and for volume it will be 3 times. Now let's look at why thermal expansion actually happens, and let's look at a very classic problem which tends to confuse students a little bit. We have a square or rectangular plate with a hole in the middle, a cavity, right? So this all is made up of the material and the hole is empty. How is this particular object going to look as we increase its temperature? So obviously the rectangle is going to increase in size, but what about this hole? Will the hole start decreasing because the net area has to expand, or will the hole start increasing? So to be able to answer this question, we need to fundamentally know why thermal expansion occurs. So when we have two molecules or two atoms near each other, the general potential energy curve is something like this, right? So when they are quite far apart, the force on them is towards each other, it's attractive, but when they come very close, the force between them is repulsive. There is a particular sweet spot which is known as the equilibrium distance, where the forces are minimum and where the potential energy is minimum and the forces are zero. The attractive forces balance the repulsive forces. This is true for any two atoms or any two molecules in any object ever, right? So they are generally at a particular temperature at a particular radius of equilibrium. As we increase the temperature, these molecules start vibrating, which changes this potential energy curve and ends up increasing this R equilibrium. So the equilibrium distance between two atoms itself changes. What that means is, when we thermally expand something, the distance, this is a very important point, between any two points increases. Right? So let's say you were saying that when we expand it, yes, the outer rectangle will expand, but the inner circle will contract. That would not really work because we want to look at this atom or molecule and the one right next to it. As we increase the temperature of this object, the distance between these two should increase. If the distance between these two is increasing and the distance between these two is increasing and so on, then obviously the circumference of this circle has to increase. So when we enlarge it, we will simply get a bigger rectangle with a bigger hole in the middle, right? So the way to remember that is that whenever thermal expansion occurs, thermal expansion is just like photographic enlargement. You just take the particular object and you rescale it and you increase the size of it. You don't worry about, okay, the area should increase of the material and so the area of the circle should decrease to keep in balance. None of that nonsense. All you need to do is, this is the original object, we just increase the size of everything because the distance between any 2 points increases. So this is how it will be a little bit later. Right. So yeah, one last thing is remaining in thermal expansion, that is the anomalous expansion of water. So what that says basically is that we know as we heat water, just like any natural object, as the temperature increases, the volume increases. This implies that alpha, beta and gamma are positive, right? This is the general case. But there are some specific conditions in which increasing the temperature of an object actually results in decreasing of volume. And one of those cases is water when it is between 0 degrees centigrade and 4 degrees centigrade. So during this time you would expect that when water is heating up, the temperature should increase. But actually that is true for beyond 4 degrees centigrade, but from 0 to 4 degrees centigrade, the volume actually decreases. And water has the least volume and the highest density at 4 degrees centigrade. So from 0 degrees centigrade to 4 degrees centigrade, gamma of water is negative. This is quite rare in nature for materials, but for water it does seem to happen. If you want to check this out in any particular way, what you can do is, you can see that you can put some very cold water in the freezer, you can put some very cold water in a bottle, look at the mark and put it in the freezer, and once it is frozen, you'll be able to see that the volume of the ice is actually greater than the volume of a very cold temperature of water, right? So between 0 and 4 degrees centigrade, as we heat water, its volume decreases, its density increases. After 4 degrees centigrade, the behavior is completely normal. As we increase the temperature, the volume increases. This has one very fascinating application, and some people have argued that that is one of the reasons why water is essential for the sustenance of life, and why whenever we look at other planets and we are searching for life, the first thing we look for is water. And the reason for that is this. Let's assume this is a lake, right, which has a lot of water. Now as the temperature decreases in the winters, the water tends to become colder, right? So how does this really work, heating? We'll study heat transfer in more detail in the next video, but all you need to know for now is the upper part becomes cold first. It loses heat to the atmosphere, right? As the upper part becomes cold, its density increases, because by and large, generally when things become colder, they become heavier. Their volume decreases, their density increases. So this water becomes colder, so this particular layer of water will go to the bottom because its density is highest. We've studied fluid dynamics, denser objects are at the bottom, right? So then the next layer of water will get cold, and then that will come to the bottom, and the rest of the water will rise up, and in this way all of the water will basically become a particular temperature which was lower than the initial temperature, right? Now let's assume that that is the situation at 4 degrees centigrade, right? It was, let's say, at 20 degrees centigrade, and by this process it lowered down to 4 degrees centigrade. Now again this particular topmost layer of water is going to become colder. If there was no anomalous expansion of water, then as it became colder, it would have become denser, it would have gone to the bottom, the rest of the water would have gotten up, it would have frozen, and that would have ended up in the whole lake being frozen. And what happens when the lake is frozen? Every single living organism inside the lake dies. But because water has this peculiar property, after 4 degrees centigrade, the upper layer of water becomes colder, but it becomes lighter, not denser. Because as the temperature decreases, the volume increases, the density decreases. So after 4 degrees centigrade, let's say the temperature of this topmost layer of water lowers down to 3 degrees centigrade. If water was behaving normally, now this 3 degrees centigrade water would have been denser than the 4 degrees centigrade of water. It would have gone down, the rest of the water would have come up, and the process would have gone on similarly. But 3 degrees centigrade water is actually less dense than the 4 degrees centigrade of water. So it stays on the top. It doesn't go towards the bottom, it just stays on the top. Then it turns to 2 degrees centigrade, 1 degree centigrade, finally 0 degree centigrade, and what happens is the topmost layer of water freezes. And now again we'll study heat transfer later, but what you need to know now is that ice is a very poor conductor of heat. That's why you have Eskimos who build houses with igloos, because if you're living in a house made of ice, you cannot really feel the cold outside because ice does not really conduct that heat well. Right. So 0 degree centigrade, this will freeze, it will stay at the top, and the rest of the water downstairs will all be at 4 degrees centigrade. So in this way, even, of course this is only valid to a certain temperature. If we decrease the winter temperature to minus 100 degrees centigrade, then it will all freeze up eventually, because ice still does conduct some heat. But for certain small temperatures, very low winter temperatures, in most lakes, the topmost part will be frozen. But below that, it's all water and life is thriving there. Right. So this is one of the major uses of the anomalous expansion of water. This completes our topic of thermal expansion. Thank you.